Hello everyone, I'm Chupao Lin from Photonics Research Group at Ghent University. In this video, I'm going to introduce our recent published paper in Nature Communication entitled UV Photonic Integrated Circuits for Structural Elimination Autofluorescence Microscopy. Firstly, let's see how the structural elimination can enhance the resolution of a microscope. Let's say we have an object which is a one-dimensional grating. It is made of metal grating and covered by a layer of fluorescence dye. The dye will emit visible fluorescence under the excitation of UV wavelengths, and the grating pitch is smaller than the resolution of a microscope. Then with conventional uniform illumination, we can only see a constant intensity in the field and no modulations coming from the fluorescence grating. Then we switch to the structural elimination. We start to see the Murray pattern. It is the pattern of the frequency mixing between the structural elimination and the fluorescence grating. And it is not the pattern of a structural elimination or the fluorescence grating. To reveal the mechanism behind, we switch to the Fourier domain. In the first case, with uniform illumination, we are unable to resolve the oscillation feature of the grating because we cannot collect the frequency of the grating, and because the spatial frequency of the grating is larger than the maximum frequency which can be collected by the microscope system. Then we switch it to the structural elimination, or the frequency will be shifted by the spatial frequency of structural elimination. And the signal of the fluorescence grating will be shifted back inside the supported bandwidth of a microscope system. By knowing the parameter of a structural elimination, like the phase, the orientation, and the spatial frequency, we are able to recover the true signal of the fluorescence grating. The current structural elimination includes a standard conventional microscope and a module to generate the structural elimination. But currently it can only work at visible wavelengths and it's bulky. In our approach, we are proposing UV-compatible photonic integrated circuits to replace this module and reduce the dimension to a size of 5 cm by 5 cm. And more importantly, we can extend the working wavelengths from visible to the UV wavelengths. This work, we use a laser operating at a wavelength of 360 nanometer as an example to demonstrate this concept. Here we show the layout of the UV peak. The UV peaks are fabricated on the aluminum oxide platform, where we recently report a low loss of 3 dB per centimeter. And the circuits are designed to generate the structural illumination over 3 different orientations, rotated by 120 degrees. And it can be divided into 3 parts. Each part contains a MMI beam splitter to split the beam into 2. And the grating coupler will couple the light from the on-chip guided mode to the far field and generate the structural illumination. The phase of the structural elimination will be controlled by the on-chip thermal phase shifter. In the experiment, we succeed to measure a high visibility of 0.9, and then we used this fabricated UV peak for the structural elimination microscopy. Here we show the configuration of the setup. The sample prepared on the microscope slides and placed below the microscope objective at a working distance to be imaged. This is just a standard protocol for the fluorescence imaging. Then we add our UV photonic chip just below the microscope slides, and the generated structural illumination will excite the fluorophore inside the sample, and the visible emission will be collected by the microscope objective. In this way, the UV peak is working as an add-on module and require no special requirement in the sample preparation. After taking a series of raw data and perform image reconstruction, we are able to obtain the super resolved scene image. And here we can see the strong clear resolution enhancement in the super resolved thin image by resolving more features in the middle part of the spoke target. And from the intensity profile along the solid circle, we can see in the wide field image, we can only see the averaged beam profile, and by contrast, we can see strong oscillation features in the thin image. After determining the minimum resolvable spacing in the wide field image and the thin image, we succeed to have resolution enhancement by a factor of 1.8. Furthermore, we have applied our proposed method with biological cells. Here we image the autofluorescence of a MADH molecule inside the yeast cells. Similarly, we can resolve more features, especially highlighted in the area, and from the intensity profile along the segment A and B, also verify this clear resolution improvement. With this sample, we estimate a resolution enhancement by a factor of 1.6. To conclude, we have proposed and fabricated the first UV photonic integrated circuits for the generation of a structural elimination with a high visibility of 0.9. And we have also demonstrated UV photonic integrated circuits-based structural elimination microscopy and achieve resolution enhancement by a factor of 1.8. And more importantly, we have validated the concept of label-free super-resolved imaging on biological cells. If you want to know more details, you can find our paper here.